Um,
And Sam, let's go for something like half an hour. Okay,
okay.
great.
Okay, so last time I mentioned okay, this is the drift chapter. I mentioned that this start off with the idea of testing two different samples using what's called the goodness of fit test. I think I mentioned that. Um, yeah, basically what we're going to do is to measure the distribution difference, um, and then I'll go into like the different types and what they test. But either we have a bivariate sample, not bivariate sample, a sample of we have two samples basically of labels y and possibly multivariate data x, and then each of these is from potentially from two different distributions p and p hat, and we're trying to decide statistically whether p and sorry not p and p prime, whether these two distributions, then again these may be from two different data sets, are appear to be different, and if they're different, that's an indicator of drift. Um, so okay, so that's kind of where we stopped off. And again, the idea is that we're not concerned just with measuring whether these two data samples are different, but whether like the populations that they represent samples from, whether those like statistically may be different. Okay, so and okay, right, and then I said that these are called two sample tests because there's testing between two samples, whether they're equal or they're similar in some aspect, as opposed to, for example, a standard t-test is a one sample test where you want to test whether like the average of a value of a sample is equal to zero or something like that. So we're comparing two different samples to each other rather than to a fixed baseline. Okay, so I just kind of mentioned a few of these tests, and that each of them
So,
yes.
so Sam, you're comparing the two distributions.
Yes, so right. So I started the
Some
easy
statistics of the
no no
distribution.
no no two different distributions based on the sample. So that
Mm.
the first case, I'm going through the different cases because the types of tests are different. This is the first case is a two sample distribution uh, on X, where the X are like the explanatory variables, not and as opposed to Y, which I'm going to treat as a categorical variable in this case. But here I'm going to start off with the example where is a univariate variable. And again, if y itself is also numeric, then you can use the same test on that. Does that make sense? So for now, it's just two numeric samples.
Yes.
Right. Okay. So yeah. So again, in this case, x is a single variable. Yeah. So a single feature.
Mm-hmm.
And these are the tests that like most people
A
are.
single numeric feature, right?
Yes, these are the tests that people are most familiar with.
Mm-hmm.
Um, okay, yeah, thank you for bringing that up. So yeah, so again, usually either people are interested in testing a specific aspect, like whether the average, like a statistic, for example, the average, the mean, the median, or variances, are these the same, or they can test is the overall shape of the distribution the same. So again, depends on what you're interested in testing. Okay. Yeah. So I mentioned okay. Here's basically where I stopped. I mentioned again. There's the first few tests over here are the most common ones people know about are like the t-test. Those are for the average. There's a test for the medians, and there's a test here for equality of variances. And again, for example, the average could be different, but the variances could be the same. It could be like the normal curve shifted over, for example. So again, it depends on what specifically you're testing. There's a test for if the x are binary, then it's then testing for the average is really the same as testing whether the proportions are the same. And then there's a test called the Yates difference of proportions. This is John. This is the one we used in the Freya slices uh, uh, test, the paper that we wrote.
Mhm.
Okay, so again, it depends on, there's a test for basically any situation you want to deal with. Okay, uh, so that's the
So,
basic.
so in
Yeah.
terms of the machine learning, um, the reason I might be interested in these measures like the average or the standard deviation and so on is because they are related to things I want the machine learning system to do, right? Like,
Right. So okay, the overall case is we want to detect drift, and in this case, it's in the data. So like if the data, um, and again, there may be a machine, if there's a machine learning model on top of this, then that also that's that's um, a potential application. Again, you may want to test for drift whether or not there is a machine learning model, but if there is a machine learning model, you might want to know, like, is the data distribution, not the model itself, but is the data distribution that the model is receiving, is that changing in some way? Like if you build your model on, I don't
mhm,
know, to predict I don't know, whether people of a given income will get a loan or not, and then maybe you only predicted that learn that on maybe a data set of people with still relatively high incomes, and then suddenly you have like people with a totally different income distribution. You might not be a good model anymore or accurate. You know, you might want to know that.
yeah.
That's the idea for all of these cases. Um, okay. Yeah. Any questions about that? Okay. Um, so one thing that's important here is that, um, and I don't go into it too much because this is a uh, whole other topic. Um, and so some of these cases I like reference an external statistics book that's free and kind of basic for some of these details. Whenever you're doing these tests, typically the way most tests give a decision is on what's called a p-value. I'm sure you guys are all familiar with them. You have some kind of null hypothesis. Basically, in each case, it's that the distributions are the same, uh, and you have an alternative, which is that they're different. So either the means are the same, or they're different, or the variance is the same, or they're different. And then this p-value, if it's low, it means that that um, you reject the null, and therefore, and that there's a probability, kind of um, there's a probability associated with it. It means that if a p-value is low, it means that the data is unlikely to um, the data is unlikely to support the null hypothesis, and therefore you kind of reject the null hypothesis. Now, again, this is a whole like topic, and papers have being written about this. Um, that the issue is, again, I'm sure you guys are familiar with this, but that p-values are kind of like a lot of people misinterpret them, and people say that the p-value is, if it's 0.05, it means that the likelihood that the null hypothesis itself is true is 5%. But that's not what it is. It means it's assuming that the null hypothesis is true. What's the probability? The the uh, the the well, what's the probability that what you saw happened? Uh, I so, should I give an example of like why this is a fallacy, or why it might have an opposite?
Yeah, yes, please do.
Okay. Okay, so let's see. Um, uh, um, so, hold on. Okay. Okay. This is gonna be like a strange I hope this is like it's a little bit of a strange example, but um uh say uh say you want to know if someone is being honest, okay? And uh you discover some evidence, okay? And this evidence would be um yeah, I don't know. Maybe you want to know is your partner like cheating on you or something? Um, is this a weird example? I can't think of like a better example.
Oh, it's okay. I mean,
Okay, all right.
keep going.
So say you yeah you want to know is your partner cheating on you? Okay, so there's various kinds of evidence like this. You might discover a text or something, say a suspicious text or something like that. Okay, and various kinds of evidence are more evident, more if you actually saw something happening, that would be like more evidence that they were cheating on you, as opposed to like maybe something less suspicious, like a text or something like that. Okay, so uh, you're saying, say you discover like a suspicious text. So the question is like, uh, if my partner was not cheating on me, what's the likelihood that, say, I would discover a suspicious text or something like that? Um, so maybe the p-value is like maybe it's unlikely to happen if uh, if if the null hypothesis here is that your partner is not cheating on you, because that's kind of what you want to assume. You only want to reject that if there's very good evidence that they are cheating on you, right? So you see it uh, uh, maybe a suspicious text is uh is is not very much evidence or something like that. But it doesn't mean that by itself that it doesn't mean that the likelihood of not cheating, it's based on the assumption. Like if they were not cheating, maybe this text would be unlikely to happen. But it doesn't mean that they're not cheating, or say it's not the probability that the null hypothesis is false. It's you're making an assumption, then how likely is something to have happened. And it happened, but then you're trying to judge how likely your assumptions are. But again, they're not exactly the same thing. Um, and this is exactly the point that people misinterpret the what a p-value means. And there's other issues. But part of the reason why people use p-values is that they're you can basically like it's very easy to formulate mathematically. Like you can always say based on this assumption, what would be the distribution of this statistic, and then I can calculate it, and it usually works that way. It's harder to say like what's the likelihood of the null of a hypothesis being correct by itself. Um, so that's why people use p-values a lot of times. Uh, okay, so I talk here about alternative ways of like measuring significance. Um, and I'm not an expert in this. I just kind of came into it from when I was writing this chapter and trying to investigate what are the alternatives. So there are metrics called effect size, and a lot of them kind of look very similar to the formulas for what you would use to calculate like a test to get a p-value. But a lot of these effect sizes basically um, they don't. Again, it's an alternative way of like kind of doing the test, but they try to more closely measure what is the practical difference rather than like a p-value, because what ends up happening with a p-value is, for example, say you're trying to test the difference between two a t-test between you have two samples. You want to know, are their averages the same? So what ends up happening is basically because the variance decreases when you have a larger sample size, right? Even if the averages, even if the true means of these two samples came from are nearly this are basically the same, like 0.99 and 1, very close. If you get a large enough sample, you can detect that, that their averages are different. If the p-value isn't significant enough, just get, more data until it is, basically. Um, but in this case, like the averages might not be, the difference between the actual averages might be very small and not of practical importance. But the p-value will say, oh, it is statistically significant, so therefore the averages that our means are different, but you may not want to decide that because you might be more concerned about like a practical measure. So these p-values, these effect size metrics, which I'll mention here. There's effect size metrics for lots of different things, but they basically um, they don't kind of have a p-value associated with them. Uh, they kind of you end up basically deciding whether the difference is significant or not, or like kind of gradations of significance based on thresholds of these values, but not based on like the p-values, not based on like a probability of being uh, like that the null hypothesis is true or something like that. So for example, I'll kind of just mention this. So Cohen's D is one of these examples of a p-value of a effect size, and it basically takes the sample means and does some calculation that looks very, very similar to what you would do with a t-test. But again, the basic idea is you don't end up using this to calculate a p-value. You just kind of compare these to some uh, some some kind of fixed thresholds. So for example, for Cohen's D, like if it's bigger than, less than between 0 and 0.2, it's like a small effect size, for example. Again, it's not a probability value, it's just and again, the idea that these are supposed to be more practical measures of like how big is the effect as opposed to is it really just because you got a lot of data. Um, that's
Sam,
that's
could
that's
could
the idea.
you could you combine p-value with effect size? So,
Um,
seeing first something like seeing first if
so
it.
usually what happens, again, I'm not an expert in this, but by any means, but usually what happens is like say you're writing a paper with results, and you have a p-value. Usually, I think people are supposed to do is present like a metric of the effect size so that like the paper can know, okay, the p-value is 0.001, but was it really significant or not? So you kind of use them in conjunction kind of maybe you would use it to support your decision about the p-value, or you could also use them on their own.
Right. So it's almost like there are best practices of how you would use them in,
Uh,
in
yeah,
practice.
that's how I understand it. Yeah. Yeah, again, you wouldn't want to reject, like for example, you wouldn't like maybe if the effect size was not significant, but the p-value was very significant, you would probably want to challenge your conclusions. They might not be like really practically valid.
Interesting.
Yeah. Yeah.
But the effect side could be associated with different statistics, like for instance,
Yes. Yeah.
correlation.
Yes. And some metrics. Again, for example, I think that the correlation in itself is a effect size, like Pearson correlation. I think that is considered an effect size metric by itself. But then, you can also, for example, you can do a significance test as to whether a correlation is significant, but that test I think, will depend on the sample size, whereas the correlation, like just calculating the correlation, uh, mostly doesn't reflect like the actual sample size.
Mhm.
that makes sense.
So one intuitive way of thinking about it is a way to factor out the size effect
Uh,
of the sample.
yeah, I mean, okay, yeah, so you'll get it not quite factor out, but it kind of like reduces the spurious like influence, I guess. I
Mm.
mean, yeah, if you have more data, I guess if you okay, so I think the intuition is like if you had more data and you calculated this Cohen's D metric, like it would come closer to whatever the true value is, I guess, but it wouldn't. Whereas the p-value would just so okay, so it's okay. You get more data, you kind of converge, but with a but to a true value, but as opposed to like a p-value might like you'd also kind of converge, but in a way that might not be like practically significant. So yeah, so the idea is it's supposed to keep keep things as significant, kind of regardless of the sample size.
Mm.
So how do we use this for machine learning? You're going to have a training set, and then you're going to get new data, and you're trying to decide whether the new data fits the what occurred with the training set. And then
Yeah, so that's the case for all of these kind of tests. Basically, again, in this case, what I've been presenting are the are univariate tests, and you know you could tell whether okay, you could tell whether like again if it's a univariate if you just have a simple example where it's a single variable and you want to test if your data distribution changed, you could perform a goodness of fit test. Or you could the other thing is again if the univariate if instead of a like a classifier, if you had a regressor, um, like where it's just predicting a numeric value, you could also test maybe if the distribution of the I don't know the predictions are have changed. Again, under the assumption that the input data itself is actually that's not really accurate, I guess, um, because if the model is like the model is I guess you could do that. Sorry, let me back up. If a model is like deterministic because if you give it the same inputs, it should give you the same like roughly the same output. You know, if it's a categorical or numeric or whatever it is. But if yeah yeah I guess if you assume that the okay yeah so I guess the main use here would be testing whether the input data have changed.
so if you find that it changed, do you just say, "Oh, I guess we can't use this," or is there a way to adjust it so it accounts for the drift, or maybe that's the next thing to go attack, right? I don't know.
Well, I think that's it's hard to answer that question because it really would depend on what you're doing. Some models, like again, I'll give you a simple example. Say you have if you have a linear regression, okay, and it's possible that say for example you had a linear regression on people of age 40 to 60, and there's a y variable, okay, that you're doing a linear regression y on the age, right? If the same relationship exactly holds for people in a different who are between 20 and 40 as opposed to 40 and 60, then your model like still works because the relationship still exists. But it might not always be the case. And you might, yeah, you should be, at the very least, you should be aware of it. You might not need to like retrain, or maybe it represents there might be some fundamental change in the data you're receiving. You know, like the classic example, not classic. I always use examples for like medicine, but like you have you have a your mammogram detector of like cancer tumors is trained on a certain kind of mammograms and then, or a certain kind of population, and then is trying to detect tumors on people from a different population. And if you don't know it, if you're not aware, it might not be working as well. But it really depends. Basically, the answer is you might need to check something.
Yeah, no, I understand. But basically, what you're saying is you can detect whether something has drifted, but then, depending on what you're trying to do, it's not a simple thing to just adjust it. You really have to look more closely at what it is you're trying to accomplish with the machine learning.
Yeah, I'm sure yeah. I mean, obviously there are examples of like some continuous kind of learning scheme where you constantly update or things like that. But yeah, I guess we're just trying to like detect whether something's changed as opposed to just automatically adjusting to the newest data.
But even, if you try to train continuously, then you might use data that is coming from different distributions and get a result that is worse, actually, right? I mean,
it could be.
So you really need to identify the drift twice in order to get a good sample for retraining, Once, so if you have some drift identification mechanism, and I know that I identified it in TFS and then in T1,
Mhm.
and maybe maybe heuristically I'm assuming that in between there was no drift, then that time window is stable, so to speak, and I can use it for learning.
Yeah, okay. Right. Yeah.
It would seem like maybe an application would be where over time things change, and how you'd want to use this is to maybe throw away older training data, right? Because it's no longer relevant, right? And just use the newer stuff, right? But you'd have to figure out at what date you want to throw it away from, right?
Exactly. Exactly. Yes.
Uh, yeah, I agree. I think that's a maybe we should deal with that. I mean, that's a whole topic, I guess, in its
Yeah.
own.
Maybe we should deal with it as well in the book.
Right. Yeah. I mean, later on in this chapter, I talk about sequential drift as opposed so not just testing two samples against each other, but like testing. I guess in an online setting, you'd be getting data kind of over time, and you want to detect as soon as you see something. Anomalous. So in that case, there's ways to, I mean, depending on the method, some of them kind of have like discounting, or like have like moving windows. Um, uh, I mean, again, those are drift detectors, which are different than than kind of updating a model, but at least you can tell whether you're not keeping all the data necessarily. You can just kind of test whether like there was a recent change as opposed to a change, relative to like the first window.
Mm-hmm. Okay, maybe this is great. Maybe it's a good point to stop, Sam.
Yeah, sounds good.
Okay, very nice. So Any other questions or comments at this point?
Maybe one more
Yes.
point to take to keep in mind that many ways to detect differences between data sets. And when we speak of drift, one of the things that we are interested in is whether it's not close enough to the new data is not close enough to the original data. So we might try to examine alternatives such as, for example, mutual information and other, which there's a whole set of methods for doing that. I don't think that we should do that. We should use those methods, but we should keep in mind that our audience may be aware of them and might ask the question, why do you use this and not that? So we might want to look at those methods.
Mm.
Is that like almost like a two sample test, or like for like a multivariate?
It can serve in such cases. The naive methods, for example, like measuring the entropy and so on, might not work well for such cases, but there are more sophisticated cases that can work in such cases as well.
If you could, I'd be happy if you could like send me a reference or something.
Sure, I'd be happy to do that. Not directly on my desktop, but in a few minutes, I'll find exactly those.
Yeah,
relevant
sure.
ones.
Great. Do you think also about something very basic like KL divergence?
That's a possibility. I was not thinking actually about something specific. I just, I had an idea. We are looking at the differences. Drift is difference, in fact. At some point, it's too different, so we should do something about it. But I can measure differences in many ways, and that was the main comment.
I see. Okay, good, very good. So thank you very much for joining today, and we'll continue next week.
Thanks, Eitan.
Thank you.
Thanks. Bye-bye.
Thanks.
Bye-bye.
Bye-bye.